I'm pleased to present here today Aldo Reyes, who is also part of the Photo2Fuel consortium. He works for KNEIA, our partner for communication and dissemination, but also Aldo has more than 10 years of experience in the management and coordination of R&D projects and innovation. Aldo is based in Barcelona and holds a degree in chemistry, a master in project and innovation management, and PhD in catalysis, photocatalysis, and nanomaterials, awarded by the University of Liverpool. And today he's going to present a little bit his insights on the roadmap that we are creating towards photo-driven CO2 valorization for the Photo2Fuel project, just beyond what is actually happening after the project's finished. So thank you very much, Aldo, to present here today. I leave the floor to you to present your insights here. Thank you very much for coming.
Thank you very much. This is basically the summary of the presentation. So starting, please allow me to start with the bad news. CO2 emissions. This is not an unknown problem for everyone. Here you see in this chart the evolution of the CO2 emissions in the last 120 years. You can see especially after the 50s, when the big industrialization time started, CO2 emissions dramatically grew up. If this trend goes as it is right now, predictions allow us to think that a number of effects will happen: oceans acidification, the corresponding impacts in biodiversity, global warming, etc. But importantly, focus on this parameter. Predictions tell us that the temperature of the planet will rise around 3 degrees. The good news is, relatively good news is, that initiatives such as the valorization of CO2 can reduce these 3 degrees down to 1.5 if the trend of valorized CO2 keeps going as it is. Just as an anecdote, you see here on the graph at the very end, there is a little drop down on the CO2 emissions. Do you imagine what is that? COVID, exactly. Industrial activity stopped massively, emissions dropped down, but we did learn nothing from that because you can see that they raise up back again. So, yeah. Now, regarding the CO2 valorization, certain industries are already adapting these new methodologies, these new technologies, okay? Basically, in big numbers, globally, between 200 and 500 million tons a year of CO2 are being revalorized. This is good news, but again, let's put it into context. On the right side of the slide, you see, well, on your left side of the slide, you see a table with a few regions of the world with their calculated, reported annual emissions of CO2 in millions per ton. So if we make the numbers, you see that the million tons of CO2 emitted a year are considerably high to the ones that are revalorized. If we do quick calculations, this is less than 100% of the emissions being revalorized, which is good news, but we see that there is a big range of improvement on this. Keeping on with the good news, okay, here is a quick summary on the evolution of how major industries are demanding CO2 for using revalorized CO2 in their processes. This is only a trend seen in the last 25 years. You can see it's slightly going up, but not also the demand of CO2 revalorized in mature industries, but also the investment. In this case, we show here the venture capital, which is referring to private capital invested in these initiatives, is higher than $1 billion between 2015 and 2023. The specific sectors on this venture capital is being invested is fuels, building materials and chemicals, and other plastics. which is basically very similar to the numbers that we saw before from the presentation from Vanessa. This is actually very good because if we have an utilization for this CO2, it means that we have a purpose to capture this CO2. This makes this economical viability a lot higher. Using CO2 as a feedstock, well, as you have seen during the day, a lot of different products and applications can be numbered for CO2. But then if we have so many different options, why we don't use CO2 a lot more than we do? Well, there's challenges, as everything in life, and the big challenge here is that CO2 is a very, very stable molecule, okay? What does it mean? That in order to make CO2 reactive, we need to overcome different barriers, and usually, industrially, the pathways done for this conversion are thermocatalytic, based in temperature, using temperature as an energy source, electrochemical, basically using an electronic current, having someone else for doing it for us, biologically, basically we use bacteria, and photocatalytic. Photocatalytic, basically using the sunlight. The challenge is not only to have an optimized pathway using these technologies, but also to have a synergy among them in order to create an optimal process for any industrial production that we want to do. This table shows very quickly a list of products being produced by using valorized CO2. Here, I would like you to put your attention, please, in the TRL 5. The last one, you see acetic acid. It's in green. If you go to the key on the right side of the screen, you see it's microbial conversion. What this table is telling us is that nowadays, acetic acid production using valorized CO2 is mostly done via bacteria. Of course, as I mentioned before, we need some energy source in here, so this could be thermally enhanced, and as we are doing in Photo2Fuel, could be photocatalytically enhanced. For those of you who are not familiar with it, this is our friend acetic acid. Mostly is produced industrially via thermal catalysis using a rhodium-based catalyst, which making a reaction between methanol and carbon monoxide, we obtain acetic acid or the acetate monomer, which will allow us to have more products on the value chain of the process. Also, it can be produced via reduction of CO2 with electrochemistry, and as I said before, via fermentation using bacteria. Acetic acid is used as a platform chemical for a broad number of other products, such as dyes, inks, coatings, and used in the food and beverage industry as a stabilizer. So, all the information I've provided bring us here to our project, Photo2Fuel. Here, this is the schematic view of what the project aims, and the roadmap we will show you in general terms today is focused on this, the production of acetic acid via photo-driven processes. In order to structure the roadmap, we have established three different, let's say, steps. First, good optimization of the laboratory scale and of the system. Then, passing to a pilot scale in which the system will be adapted and we will have some upgradings proposed. And finally, a vision on how the industrial production and automation of this process can go. Here, we will show you also three different parameters. The impact inside the enterprise in the project, which will refer to how these proposed actions will impact in the project itself, meaning that they will act as enablers for further steps. The costs and investments, here is always a relative cost based on the comparison from step to step, For example, it's not the same investment to have a chromatographic analysis of something compared to building an entire plant for something. And then the novelty level. Novelty level meaning that we could take actually knowledge, I mean, new publications or articles or share different novelties from the project. So if we start with the short-term strategy, okay, the laboratory strategy, first thing, and you have seen over there, is that we have to know exactly how the band alignment, how the photosynthesizers work with the cell. So here, a series of actions based on the optimization of the interface, the engineering of the interface, in order to enhance the charge transfer, goes on. Here we mentioned optimizing the band alignment, the light harvesting, the quality of the light for the process will be very important, and of course, optimize the surface functionalization. Also, when we are having this process, as in any chemical process, we usually have some side reactions, so the production of secondary products. In this case, we want to highlight the reactive oxygen species that can be formed from the photochemistry itself, like radicals, that can actually delay the reaction we are interested on, can actually compete with the reaction, or can even degrade some of the photosensitizers we are using. So minimizing the production of these chemicals could be very interesting, and here we mention a couple of strategies based on the protection of the catalyst using hydrogels. Also in some other publications we have seen they propose silica alumina, and also to have the catalyst surrounded by a physical barrier such as MOFs, anchored to MOFs, and then use the MOFs also as a catalyst. Also at the laboratory scale, well, the reactor design and the irradiation needs to be optimized. Miniaturization concepts, taking into account that if we go step on the process, this miniaturization will need to be adaptation to the further scales that we are using, either pilot or industrial. Of course, this will bring also needed optimization of the light distribution, the gas exchange, and of course the financial, let's say, challenges associated to that. And finally, at the laboratory scale, we cannot forget about the main actor, let's say, of the reaction, which is the cell. So optimizing the cell growing and cell viability will be key. We propose to use more time resolve spectroscopy in order to know exactly at real time or as quick as we can any changes in the metabolism of the cell, and the identification, of course, of the bottleneck reactions, meaning that the reactions that can compete with ours or that can actually affect the viability of the cell. Going to the pilot sketch, so we go one step further. Now we need to think on the liter scale, not only at the microliter as we were doing, milliliter, sorry, as we were doing before. Here we need to first think on the scale of the biohybrid preparation and how we protect these processes. So now we need to produce more of the catalyst, how we do it, and how we make this catalyst ready to go into the reaction. We need to define also the encapsulation systems if we adopted it from the previous steps, and how we anchor this to the reactor. Here also will be very interesting to start analyzing how these synergies between energy sources can be used. We can start proving mild thermal conditions and electrochemical synergies with the photoreactor. Also, the CO2 supply here is very key, since we need to adapt also the gas-liquid transferences that we have, since the scale has gone up, but also how we can implement continuous feeding of the CO2 to the reactor with the proper, avoiding of contaminations and things. Also going on the midterm strategy, we propose here the inclusion of inline sensoring for the monitoring of the process, for the monitoring of the different key parameters of the process, and also thinking on how can model and design this continuous or semi-continuous testing for the process going over time. Also the implementation and starting the planification of further steps of the purification methods, which will be very important for the products that we finally achieve. And of course, we have to include the analysis for the cost associated to the process steps, post and pre-steps, meaning that, for example, what kind of CO2 will I use? Is it better to start thinking on having an auto-capturing pilot plant next to my reactor, or is best to buy always the CO2, which quality of CO2? So all these kind of steps need to be taken into account here. Once we have all this clear, once we have demonstrated that we can produce the acetic acid in the conditions that we want, now we propose some industrial pathways, some actions for the industrialization of the process. First of all, we want to focus on the design of the photoreactors. It will be interesting to include some modular panels that will allow the process to change depending on the parameters that we rely on. For example, it's not the same to have the plant here in Seville, that you see that we have a very bright sun today, rather than have it, I don't know, in the Netherlands, in which we will depend a lot less on sunlight. Of course, we will always have a safety system based on LEDs or in lamps or something, but if we want to focus on the sunlight, for example, this will be a parameter to take into account. As I mentioned before, integrate or not units for self-supplies of CO2, for capturing the CO2. And finally, very important for the reactor, the biohybrid architectures needs to be immobilized in order not to have as less leaching as possible from the system. As for the catalytic operations, we need to think also that we need to have a production of the catalyst, not only in our process, but for our process. So in order to automate, in order to guarantee feedstock of our catalyst, we need to think on how to automate the production of the catalyst based on the bacteria. Also to take into account the post steps, which is separation and purification, and explore the combination of different energy sources for multiple product valorization. This means that if in the process we realize that we have a subproduct that could be interesting for some other chemical reaction, for some other industrial process, it is the moment to take into account this and think if this could be a potential market niche for us, if we could exploit this, if we could adapt our process, our technology to satisfy this demand or not. Then ensure, of course, the biosafety and regulatory compliance, not thinking only in the process, but also in the people who is working in the process. Take into account if we work in the future with modified bacteria, that this will bring also some regulatory aspects that we need to cover. And, of course, the analysis, techno and economical analysis of the marketability for our products. Then, talking about the commercialization and the partnership, here we need to, we propose to check how our enterprise could align with different credit carbons that we have from governments in order to cover the CO2 demand, what kind of policies and initiatives we could join to or we could ask to in order to reduce economic barriers, what partners will be key for in the chemical industry for us, again, as a suppliers or as consumers of our products. And of course, in order to engage with all this, we need to have proven that we are ready for this with predictability, competitiveness, robustness, and also have products that meet the quality of the market. Other parameters to be considered that are not tabularized here, but during the process they will come up because this is a process that will evolve over time, is the additives. Do we need additives? Do we buy them? Do we get them from other industries? Do we partner with someone for exchanging this this process for another one? Chemical quality. Do we need to buy pure CO2 or almost pure CO2? Is better to have a small purification plant next to our reactor in order to directly feed this CO2, etc. The same for our our products. What kind of quality do we need for the market? Chemical quality as well. We need to clean the reactors. What kind of products, chemical products for the cleaning do we need? Will they have any chance of remaining in the reactors in order to condition our process? So we need to think all about this. Product separation, exactly the same. What kind of products are interested on? What kind of membranes do we want? Do we want a face-to-face separation, etc.? Transportation and storage, more of the same, regarding the CO2 and also regarding the products that we have. Other driver markets, well, this is an everyday changing parameter from geopolitical considerations up to any other driver that can make the market fluctuate. If we take this into account, probably the financial and environmental profitability of our process will increase. Other challenges and open questions, here is just more food to thinking. Do photo-based technologies have a real chance against what is already established in the market, in industry? How will the international and European policies evolve together with these valorization routes? Will the technology run at the same pace as policy? Will they, be at the same time ready for being used? What kind of enablers and new blockers will we have during journey? Maybe in 2 or 3 years we have our colleagues from ICAS or from Uppsala describing a new artificial photosystem 2 that can be used for something. So these things will make evolve this roadmap as well. And then finally some calls to action that are actually currently ongoing. The purpose and the motivation that we have is the CO2 levels are records. We need to do something. Multidisciplinary collaboration is key in here. Dedicated funding, as we have seen from previous presentations, is already going on. And then policy alignment and regulations need to be increased in this sense. And I just want to finish with this last message for everyone. Thank you.
Thank you very much, Aldo.